is integrable, you will be able to find the surface for sure if and only if. So it's two-way condition if it's involutive. This is extremely easy statement. Involutive, that the Lie bracket will not provide anything new, implies integrable. And it's if and only if goes both ways. If it's involutive, it's integrable. If it's not involutive, it's not integrable. Why this is powerful? Let's see. Because simply, here is the problem that we will be able to solve. Given some collection of vector fields, x1, x2, and so, okay? Just bear with me for a minute, please. Given some vector fields, okay? And you're asking that legitimate question that I asked. By flowing these vector fields only, by flowing these velocities only, will you be able to cover the whole space, or you will be living on a smaller dimensional space, okay? Now, the answer is extremely easy. Given this collection of vectors, please collect them in something we call distribution. And then check involutivity. How can I check involutivity? It's very easy. Compute the Lie bracket between any xi and xj. The result should be also in delta. The Lie bracket is very simple computation. It's not like solving PDEs, right? So I can do that. It's extremely easy. And if it's in delta, it means what? It means that it's involutive, okay? And if it's involutive by Frobenius theorem, means that the delta is integrable. Integrable means what? That there exists a surface that you can integrate. Okay, let's have an example. We'll continue with that example. So I have x1, that is y negative x and 0. I have x2, that is 0, z and negative y. And I have x3, that is negative z, 0 and x. And these are three vectors, velocity vectors in R3, correct? Okay. Are they independent three vectors? Actually not. Why? Because actually at any point P, x, y, z, we have what? We have z times this guy plus x times that guy plus y times this guy is 0. So at any point, x, y, z, any point little x, y, z, just bear with me here, at any point. Say maybe x, y, z are 1, 2, 3, okay? So at any point, you have this relation between the three vectors, so they are not linearly independent. One always depends linearly on the other two. So if I collect these guys, here is my delta. The span of these guys, x1, x2, x3. What is the rank of delta? What's the rank of delta?
Less than 3.
Yeah, how much? You always have two independent vector fields, and the third is dependent on them.
2.
So the rank of delta is 2, and it's always 2, luckily. So it's regular distribution, it has constant rank. So if this is blue, and this is red, and this is green, and this is R3, X, Y, and Z. You guys know that here is the blue, it's like flying westward. And the vector field is defined everywhere. If you go here, it's something like, this is the guy, okay? It's defined everywhere. The red is something like this, like that, okay? And the green is here. So you can see now, please look here with me. You can see that at any point, this point for example, I have two linearly independent vectors. So here is my, if you collect them together, they form a plane. Over there I have two independent vectors. If they collect them together, they form a plane, and so and so. And I'm asking this distribution that forms a plane everywhere, which is part of the three-dimensional space, is it really integrable? Can I integrate it? These are velocities. Can I integrate it to get a surface out of that or not? The answer is very simple. How do you check it? Well, you have three vector fields in your collection. Check the Lie bracket between any two. Last time we did already the Lie bracket between x1 and x2, and this is actually how we found the third vector. This is x3. And in fact, if you do x2 and x3, you will find that the Lie bracket is simply x1. And finally, 3 and 1, you will find that it is x2. Just try good exercise for doing the Lie brackets. So whenever I do Lie bracket between any two vector fields in the collection, the result is not a new vector field out of the collection. It is contained in the collection. Okay? It doesn't have to be exactly one of these, but it should be at least in the span. Okay? So linear combination of them. So if you do that for every vector field like we did now, this means that what? Delta is involutive by definition. Why? Because the definition of involutive is when you do the Lie bracket between any two, you get something in the delta. Okay, delta is involutive. This is by itself is not very useful. But luckily, through this theorem, now, through Frobenius theorem, Frobenius says that if it's involutive, this means it's integral. Delta is integral. What do you mean by integrable? It is the definition. By integrable, you mean that there is a surface really that I can integrate. There exists n in R3 such that delta covers the tangent space. Okay? Delta at any p is the TPN, or equivalently, these vectors, there exists a surface such that these vectors are always tangent to that surface. In fact, they form the tangent space of that surface. Any question about the geometrical meaning or about how to check things?
Under such conditions, how would the distribution be not a normal distribution? Like if it's the vector fields are like this,
No, just a second. Say again, please. How the distribution
cannot be a normal distribution.
normal?
With the normal rank, like it has one rank at one point and the other rank at the other
Yeah,
point.
simply if I erase this guy, my delta is the span of x1 and x2 only.
Okay.
These guys, any point along the x-axis, all these points,
It's by
it's what? 0 something, depends on the value of x, 0. Okay? So this gives you a vector in the y direction, and this will be a 0 vector. So at some points, at all the other points except the x-axis, will give you a plane, but
Here it gives
the
a line.
x-axis will give you just a line, right? Yeah, simply one of the vector fields vanish. So this is why sometimes you need to have extra in order to apply the Frobenius theorem. I'm not going to test you on these.
So you mean to say that if in a 3D space, if a vector covers only one direction, then it can be a vanishing vector, otherwise not?
In 3-dimensional space,
If we are checking the theorem just because we are not having the 3 linear independent. If there are 3, so if 3 is why you are
worrying. 3 linear independent vectors.
Then why you are checking? So if we have 2, and out of those 2, they both have the 2 components in it. Like they cannot vanish at a point. So probably it's going to be a normal distribution.
What do you mean normal distribution?
What do you call it?
You mean regular distribution?
Yeah, regular distribution.
Okay, yeah. Yes, you.
So because it is a plane, and then it's usually defined by 2 vectors, or at any point by 2 vectors. The rank in this case is always 2. Right?
Yeah.
Okay.
So I'm allowed to apply the theorem, because the theorem requires that your distribution is regular. If it's not regular, I will not be able to apply the theorem. But all the problems that we're going to have for regular distributions for this course. Yes, Joseph?
How come it doesn't go away at the origin?
It goes away at the origin.
It
so
does?
this is for constant rank for all points except the origin.
Okay, except the origin.
So you guys think that this is obvious. You have here a plane, you have a plane at each point, so why not integrating these planes and get surface? That this plane is always tangent to that surface. In other words, I have 3 degrees of freedom, but I'm allowed only 2 velocity vectors at a time. So it makes sense that since I only have 2 velocities at a time, independent, I cannot achieve 3-dimensionality. And I'm just only living on a smaller surface. Actually, this is not the case at all. So last time we had the problem of the rigid body, and we analyzed the case where I have only roll and pitch. Right? So the rigid body has 3 degrees of freedom, roll, pitch, and yaw, and I was only allowed to do either roll or pitch. These are the allowed velocity vectors, correct? The allowed velocity vectors only. So I don't have any direct velocity vector in the yaw direction. Yet, through this Lie bracket thing, we saw that the Lie bracket between the roll and pitch was the yaw. It's a new thing. So if you have a distribution that is the span of the roll and pitch, this is 2 independent vectors living in 3-dimensional space, but actually you cannot integrate that. Why? Because the Lie bracket between roll and pitch is yaw that is not in the depth. We'll do something more general now to clarify this. And although this is not our goal, but it's good to have some relation with mechanics finally. Our goal will be the next week. So in mechanics, we know that we have holonomic constraints, right? What do we mean by holonomic constraints? Is that the constraint is on this form. Psi k is function of the q's only. Something like this example where we have 2 masses connected by a rigid rod. So I have x, I have y, this guy is L. The constraint is x squared plus y squared equals L squared or minus L squared equals 0, correct? You have a relation between the q's. Now whenever you have a relation between the q's, indeed you can use that relation to get rid of one of the q's. So originally I was living on 2-dimensional space, but because I have a holonomic constraint, I can reduce the problem and live in 1-dimensional space only, correct? We have on the other hand, something here like, I will call it velocity constraint in the moment. What is a velocity constraint? The velocity constraint actually, I'll give you the the technical name for it. It's called Pfaffian constraint. Okay. What is the general formula of a velocity constraint? Well, it's a constraint not on the q's, but on the q dots, right? So summation j equals 1 to n, some coefficients, and this is epsilon k, a k j times q j dot, and these guys may be function of q's, that's fine. This is 0. Like what? Like maybe xx dot plus yy dot is 0, right? This is a constraint on velocity. Any question about that? So again, if I have here 2 degrees of freedom, x and y, subject to one constraint on velocity. The question is the exact same thing. Can you do the exact same thing here? You have a constraint on velocity, not on position. If it's on position, surely I can do that. I can remove one of the degrees of freedom completely. But if it's on velocity, can you remove one of the degrees of freedom completely and live on a reduced dimensional space?
No.
Well, this depends on that,
Can we do it?
whether this constraint you can integrate it, right? I'm going to say integrable constraint, like this guy in particular is indeed integrable. If you integrate it, this is actually the derivative of this constraint, simply. This equation is the derivative of that. If you can integrate this constraint and live on a smaller dimensional space, then it's as if you have a holonomic constraint. But if you cannot, then this is non-integrable. The non-integrable ones are the ones that we know as the non-holonomic constraints. I cannot integrate them anymore to live on a smaller surface. Okay? You can start now to see what there is a connection between what we have been saying. Not perhaps you don't see yet the exact connection, but definitely there is a connection. Living on a reduced dimensional space and all this kind of stuff. Okay? Any question about this for the moment? And we're going to see in a minute how we apply this tool, which is very simple to apply it. Remember it, to apply it indeed, you just do the bracket, and the Lie bracket is just differentiation. It's very simple to apply. How can I apply this to check my set of constraints, velocity constraints, whether they are integrable and I can indeed get rid of some of the degrees of freedom, okay, and turn them into holonomic constraints, or they are indeed not integrable and I cannot live on a reduced dimensional space, which means that using this reduced set of velocities I can cover the whole space.